Okay, let's do example 4 then with a rational function. We're starting by stating the domain and range. Fine. So you should know by now that the domain of a rational function is always going to be all real numbers except for the zeros of the denominator. And the zero of our denominator here would be, if you set it equal to 0, then you're subtracting 4, dividing by 3, so negative 4/3. So that's your domain. Now the range, the rule is not quite so hard and fast, but as long as your rational function is sort of the simple variety, simple, meaning the top and bottom are both linear or constant, then we know that this thing's graph, when we graph it, it's just going to be a hyperbola, and it's going to have a horizontal asymptote and a vertical asymptote. And the branches are going to just go something like this, right? So we're going to have a range of all real numbers except for the horizontal asymptote. And I think I told you guys the rule. I told you that when the numerator and denominator had the same degree, you just take the leading coefficients. You guys are actually well prepared now to understand that better, though. Isn't the horizontal asymptote the end behavior asymptote? So essentially what you're doing is you're finding the limit of f of x as you let x go toward infinity. So you're basically doing 2 times infinity minus 1. You're dividing that by 3 times infinity plus 4. And the idea is, you know, like, I don't know if you can remember being a kid being like, you're dumb, and then like, no, you're dumb, like, you're dumb, no, you're dumb. Well, you're dumb times infinity, right? And then the other kid would totally get you because they'd be like, but you're dumb times infinity plus 1. Well, that's kind of the deal here, right? If you're already at 2 times infinity minus 1, does that really have any effect? Kind of doesn't, right? It's a drop in the bucket. You can basically ignore it. Same thing with the plus 4. 3 times infinity plus 4, like the 4 does not matter. Get out of here. And then at that point, we are so close, right? It's a limit, so it's about what we're approaching. It's not about the actual value. But as soon as you realize that these constants on the end are essentially meaningless, then you now have 2 infinity over 3 infinity. You can kind of cancel the infinities, and that is sort of the justification why the value that we end up approaching is really just the value given by the coefficients on the highest powered x values. And again, just to expound upon this, imagine if it was 2x squared minus 5x plus 6 all over 3x squared plus 1x minus 7. Imagine still letting this all go to infinity. You'd have infinity, 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 infinity. Even when you have other infinity terms, infinity squared so grossly overpowers even the 5 infinity that you can kind of let them cancel too. Now there is an algebraic way that I could justify why these things essentially are meaningless. I'm not going to get too deep into it, but I want to at least lay this sort of foundation on you that it's only the highest powered terms that are relevant. By the time you go out to infinity, only the highest powered terms are relevant, and then you can let them cancel, and the only thing that really matters is those leading coefficients. All right, hopefully that'll help that rule to stick in your head, but it's not super important. All of that was just to justify that our graph absolutely has a horizontal asymptote at 2/3, which means 2/3 is the 1y value that this function will never, ever, ever map onto. So that's the one restriction from our range. And that's it. State the domain and range of the function. Fine, we did it. Now you're supposed to sketch this thing. Well, we just talked about it. We just said that we have our vertical asymptote at the 0 of the denominator, so negative 4/3. Let me make this thing a container. Can contain anything. Alright, forgive me. So we could plot a vertical line at negative 4/3, so 1 1/3. So like here, And then since our horizontal asymptote is at 2/3, we can plot that too. That would go here. And then the only thing left is to maybe plot just a couple of points to make sure you're putting your branches in the right place. So I would probably go ahead and evaluate at 0. We get -1/4. So at 0, I'm at -1/4. That tells me that this whole entire branch is going to be here. We can see that at +1/2, we get 0. So that's our x-intercept. But for sure now, I can just sketch this whole branch. It's going to lie underneath, which does mean that the other one will be here because we know our graph has to be a hyperbola. But there should be our graph right there. And if you don't like that graph, you were supposed to get contained. Why didn't that get contained? All right, whatever. Anyway, I hid the better graph down here. There's your better looking graph. But you can see we did it right. Here we are at -1 1/3. Here's our other one at 2/3, and there's our graph. So that's a good looking graph. I'm just going to put that down there. This graph's fine. It's supposed to fit there-ish. No, lower. Higher? Yeah. Okay, whatever. Anyway, I think we did those first 2 bullets. We did our domain, we did our sketch. So now it's time to find the inverse. And this is where things get a little bit trickier, for sure. So we're on find the inverse. First of all, you've got 2 x's. So you know our first step is to switch all of our variables. So f of x is our fancy way to say y. That'll become x. But then the numerator becomes 2y minus 1. The denominator becomes 3y plus 4. And then from here, we got to isolate y somehow. So we've got 2 different y's. We've got to combine them and then isolate them. I would just throw the x over 1 and not cross multiply. We're cross multiplying. So this will be x times this, and I will go ahead and distribute the x in. So I'll get 3 times x times y plus 4x. And that's going to equal 1 times 2y minus 1. So just 2y minus 1. What I hope you're noticing now is we've got 2 terms that both contain y. We want to bring those terms together. So I'll keep my 3xy on the left. And I'll subtract 2y from both sides. And then I'm going to get rid of this term that does not have a y in it. So I'll subtract that from both sides. So that means I've got my -1 and I'm subtracting the 4x. So I'm just kind of, I'm pulling the 2y over to the left, I'm pushing the 4x over to the right, and now I'm here. And what I can do now is this y, I wish those y's looked the same, but this y is a common factor, so I can factor it out. And then I'll have y times 3x minus 2. And that's going to equal -1 minus 4x. And then, finally, we can just divide by 3x minus 2. So we get y equals the inverse function, which is going to be -1 minus 4x all over 3x minus 2. And now, if you guys will tolerate a smidge of simplification, here's a nice little trick. We're going to factor out a -1 because we hate those. Okay, and then a super handy trick that's going to come in, well, handy in pre-calc is knowing that when you've got a minus b, you can flip those terms around, right? Technically, I don't know, there's a lot of ways to think about it. Let's think of this as just a minus b is really a plus the opposite of b. So now if it's addition, you can certainly switch things around and just go -b plus a. But then you've got a leading negative, so factor that negative out, and you get b minus a. So perhaps the long story short is, if you've got a minus b, and you wish you had b minus a, if you wish you had it the other way around, that's actually a change you can make. You can just make it b minus a, as long as you understand that what that does is it generates a negative in the numerator. It makes it the opposite of what it used to be. And a more concrete way to think about that is just pick a couple numbers. Like, what's 10 minus 7? Isn't that 3? Okay, cool. So what's 7 minus 10? Well, it's still 3, but it's negative 3, right? So the fact that you changed the order in which you subtracted means you do still get the same value, but it's the opposite of what it used to be. So you can switch that order and just generate a negative. Okay, why am I saying all this? Well, because that means that downstairs I can just make this 2 minus 3x. That'll generate another negative, which super conveniently will cancel the factor of negative 1 that we had in our numerator and give us a much cleaner way to think about our inverse function. It's going to be 1 plus 4x in the numerator all over 2 minus 3x in the denominator. And to me, that's just a heck of a lot cleaner than having the negative in the numerator. That's really ugly. So if we can clean that up nicely, we ought to. So I did. But that's it. This is now our inverse function. You'll notice the inverse of a rational is another rational. That's it. Hopefully all these steps of algebra made sense. I think it's straightforward, actually. I think it's really straightforward. So look that over. Ask me questions if you have any. State the domain and range. Okay, fine. 1 plus 4x, 2 minus 3x. Okay, looking at this thing, I should be able to just do the domain and range just by looking at it. But of course, if anything weird happens, I do know that I'm really supposed to be basing my domain and range for the inverse off of the domain and range of the original. But just looking at it, it's another rational function, so the domain ought to be all reals except for the 0 of the denominator, which is, if you set it equal to 0, minus 2 divided by negative 3 would be positive 2/3. Does that feel right? Certainly should, because if we go back, wasn't that our range before? Yep. All reals except for 2/3, right? And that is now our domain. That's exactly how this ought to go. Now, what about the range? Well, our range should be all reals except for the y value of our horizontal asymptote, which is still given by the leading coefficients, which is not the 1 and 2. It's the coefficients of x, so negative 4/3. And if you were paying attention 1 second ago, when I just showed you, that is what our old domain was, right? All reals except for negative 4/3. So that means our domain and range are flipping exactly like we expected them to, so that's perfect. So where are we? I didn't move my little label guy. We're just stating the domain and range of our inverse function. I feel good about them. They're definitely right. So that brings us to the next phase, which is the phase where we have to do that double composition. We have to do it one way, then the other way. We have to show that they're equal to each other, and we have to show that they are both equal to just plain old x. They both have to simplify down, down, down. So before I forget what even is our inverse, it's that. Paste that in. Put that over there. Throw this in the bin because we're not using that. Put a little divider line and then get down to business. Alright, so over here we'll start with f composed with f inverse. This is going to get a little ugly, but you know, it happens. We're plugging the inverse function into the original, so I guess that means we're going to have 2 times the whole inverse minus 1 all over 3 times the whole inverse plus 4. So the whole inverse is 1 plus 4x all over 2 minus 3x. Okay, so like to simplify, this 2 may as well be a 2 over 1. We distribute it into the numerator only. and we get 2 plus 8x. And that thing is all over 2 minus 3x. Then this 1 needs that common denominator. So you can think of this 1 as being 1 over 1, and we need to multiply it by 2 minus 3x over 2 minus 3x. This by now should be second nature for you guys, generating these common denominators and combining. Should be. So we're going to go ahead and subtract. Well, if it's 1, it's literally going to be 2 minus 3x over 2 minus 3x. All right, what's happening downstairs? We're distributing in a 3, so we get 3 plus 12x. That's still over 2 minus 3x. But now this 4 is a 4 over 1. We're multiplying that by 2 minus 3x. So that when that 4 distributes in, we're subtracting, actually we're adding 8 minus 12x. And that'll be all over 2 minus 3x. And it's time now for me to admit that all along, the 2 minus 3x, that's going to be our common denominator. Downstairs, it's going to be our common denominator too. So you know it's going to cancel out, right? So we can just cancel. Our numerator is going to be really just the numerators here. So 2 minus 2, well, that's gone. And then 8x minus negative 3x is 11x. And downstairs, 3 and 8 makes conveniently 11. And 12 plus negative 12 conveniently cancels. And like we said, our denominator is going to cancel. So would you look at that? The 11s now cancel. And we see that our composition function does boil down to plain old x. And a similar thing should happen when we do our composition the other way around. So let's do, oh boy. Okay, and come back. Yep. So we're doing inverse composed with original. And that means that this time the outer function is the 1 plus 4x. All over 2 minus 3x. And so in goes the 2x minus 1 over 3x plus 4. All right, let's switch to whatever, green. Planning ahead a little, we're going to need that common denominator of 3x plus 4. So this 1's going to get multiplied by that 3x plus 4. But I'm going to plan way far ahead and say that these denominators are going to cancel out again, just like they did over here. So I'm really only concerned with my numerators. So I'll get 1 times the 3x plus 4. That'll be a 3x plus 4. Then I'm going to be adding to that this 4 distributed in here, so 8x minus 4. Then in my denominator, again, the 3x plus 4 is a common denominator. That's going to get multiplied by the 2, so that'll become 6x plus 8. And then that'll be minus the 3 distributing in, so minus 6x and plus 3. And again, where did the denominators go? Well, they're the same denominator. The 3x plus 4 in my denominator and the 3x plus 4 in my denominator down here, they would cancel out, giving me this back. So I believe now we can just say that the 4's cancel, and I again get 11x, like I did before. And then the 6x's and the 6x's cancel. 8 and 3 makes 11. Cancel the 11's, and you get x. So we have proven that our functions truly are inverses of one another by composing them. And that's it. That's the end of it. Yeah, no more to do. We tackled all of it. So that's example 4. We'll run these in class tomorrow, I guess. And hopefully a few more examples. But we got to take our quiz. Tuesday? I'm thinking Tuesday. So I can maybe point you in the direction of a few more practice problems. We can do some homework problems. But we got to take this quiz on Tuesday. So whatever. Talk to you later. Bye.